We're on the third problem now. And the third problem just has two definite integrals. And I I only introduced chapter 6 to you with 6.1. And then you told me that you were good for the rest of the chapter. So that's why we didn't go any further than that um, in that chapter. But this is part of, or adding on to chapter 6. So we pretty much what you're dealing with are definite integrals. Um, and the beautiful thing that allows this is the fundamental theorem of calculus, which I think I'm going to tattoo on my right forearm. I really think it's such a powerful theorem um, because it connects differential calculus with integral calculus. That's how powerful it is. So these two facets of calculus come together from this theorem and allows you to use actual integration of definite integrals, as well as the connection between derivatives and antiderivatives and integration. Anyway, sorry, I just rambled. But the integral that we have right here is um, it can be simplified. Right? So taking a look at the what's on the inside, um, let's do some reduction of this fraction first to see if we can kind of work with an easier definite integral. So let's do that. All right. So remember from a previous section that if I have a sum or difference in the numerator and the denominator is the same, I can break it up. So this is the same thing as 3x divided by 2x minus 2 over 2x. That's the exact same thing. So if you notice, there's some reduction that we can do from both of the fractions right here. So the first one, the x's will go away. And in this case, the 2, the common factor of 2 will go away. So this is actually what this becomes. Now, again, just remember that this is a function. So you do theoretically still have a function restriction at the value x equals 0. But because the integral goes from 1 to 2, I'm not concerned about that. So I can just simply go straight forward into the integration because I am outside of the interval of where, or I'm outside of the undefined point, which is x equals 0. So in that case, I go from 1 to 2 of 3 halves minus 1 over x dx. So you can do it two ways. You can break it up, but I prefer to do the do the integration all as one. So because it makes it easier to do the computation, or for me, it makes it easier to do the computation. So in this case, I have 3 halves x, because the antiderivative of 3 halves is 3 halves x. And the antiderivative of 1 over x is the natural log of x. And I don't have to put the absolute value sign because I know that the values of 1 and 2 are positive numbers. So 1 is positive and 2 is positive, so I already know I'm already in the positive range. So I don't need to change the sign or anything like that, right? Because the positive of an absolute value is positive. And I'm going to evaluate that from 1 to 2. So 2 is all calculated minus all of 1, right? So that's going to be 3 halves times 2 minus the natural log of 2. So that's one section minus 3 halves times 1 minus the natural log of 1. Is that, yeah, it fits. Okay, good. So now what does that give me? That gives me 3 minus the natural log of 2 minus 3 halves. So the natural log of 1 is 0, so that doesn't matter. So what I really have is, so 3 is the same thing as 6 divided by 2, 6 halves. So 6 halves minus the natural log of 2 minus 3 halves. So my answer is 3 halves minus the natural log of 2. Well, let's check that. Let's see. Am I right? All right, so you're going to go to math. And we'll select down to the functional integration. Okay, so that's number 9. So I'm going to write it. I have to write it kind of weird because it's all about order of operation here. Let me go back. So let's do 3x minus 2 parentheses divided by open parentheses 2x close parentheses. So we're doing it in terms of x, right? That's what I have here. And I'm going from 1 to 2. So what number do I get? I get 0.80685, blah, blah, blah. All right. Now let me put in my answer of, I'm just going to say 1.5, because that's 3/2, minus the natural log of 2. Oh no, that says e. That's not what I want. Delete. Natural log of 2. It better be, boom, the same, because it is. No, that's good. All right, so that is your solution. 3/2 minus the natural log of 2. All right, so let's go to the next one. Let me clear this. All right, so we'll go to the next one. Oh, I already did it. Let me clear it. Clear the ink. All right, so this one is also another definite integral. So again, this one I have no simplification, so I don't have to, I don't simplify it, right? Or I can't simplify what's inside. But again, I like to take care of doing the integration all in one shot instead of breaking them up into the sum or differences, right? So in this sense, what I have to do is take the antiderivative. So remember the antiderivative of e to the kx dx from your book is 1 over k e to the kx. And of course, k can't equal 0, because then you have a constant. All right, so if that's the case, in this instance, k is 2, so my antiderivative is 1/2 e to the 2k, 2x, minus 3/2 x, and that goes from 0 to -1. Now, yes, there's a property that says your upper bound should be the higher number, but in this instance, you're evaluating it. So it doesn't matter which way you do it. You're still going to get the answer that you need. I don't know if she's asking for you to do for you to use the property and throw in negatives, but the more negatives that you introduce, the more difficult it's going to be for you to do the computation. So leave it the way that it is. You can still evaluate it. The fundamental theorem of calculus works either way when your bounds are reversed. All right. So in that case, I have evaluated when x is -1. So I have 1/2 e to the -2. So 2 times -1. 2 times -1 right here gives me the -2. And then I have -3/2 times -1. That's plus 3/2. And that's minus, and evaluated at 0. So here, when I have 0 here, this becomes e to the 0, so that's 1. So I'm left with 1/2 times 1, 1/2. And then, of course, 0 times -3/2 is 0. Right? So I'll put minus 0. Right, so let's evaluate this. This is, let's see, 1/2 e to the -2. We'll clean that up. Plus 3/2 minus 1/2. That's 1 plus 1 over 2e squared. So I took that e to the -2 and threw it down in the denominator. So let's see, what is that? 2e squared plus 1 over 2e squared. That's just, I mean, this is okay, but I mean, this is okay. They're actually equivalent. So it could be given to you in either, I would accept either answer. It's fine. All right, so let's check that one. All right, so let's see. We're going to go back to functional integration. It's number 9. So what do I have? I have e to the 2x minus 3 divided by 2 in terms of x from, what is it, 0 to -1. And it doesn't matter. All right, cool. So I have 1.06, 7667642. Okay, great. Crazy number. But I have a crazy number too. So let's see. Let's calculate this. So I have 2 times e squared plus 1 divided by 2 times e squared. What do I get? Boom! Same answer. 1.067667,642. So approximated. So it's good. All right. So problem number 3 is done. I don't think I've been on here very long, but just for the sake of continuity, I will avoid going on to number 4 because it's partial differentiation. So I don't want to confuse the two. All right. So I'm going to stop here. Review this one. If you have any questions, we'll hit you up and talk about it on the FaceTime. All right. Later.